Good morning, everyone. I'm Belhal, and I'm going to present you our paper called HWA, Hyperparameters Weight Averaging in Bayesian Neural Networks. This is a joint work with Professor Ping Li, done at Baidu Research. I will quickly go through what is Bayesian deep learning and how do we train such architecture. Then I will introduce you our new method, namely HWA, and present you some numerical results on benchmark datasets. Bayesian deep learning is the combination of Bayesian modeling and the multi-layerness of neural nets. And formally speaking, you can consider an input-output pairs of n samples, xi and yi, and a vector of latent weights that we call W, and is assumed to be distributed according to a prior distribution pattern. Then you consider your classical classification problem as a softmax of a multi-layer neural network F. And the difference here is that this model F is parameterized by the latent vector W. The training of such model consists in minimizing a Kullback-Leibler divergence between some proposal distribution Q, parameterized by theta that will move through the epochs, and the true posterior distribution of the weights P of W given the observations. This problem being intractable, we will maximize the elbow as written on this slide, and this will be our objective loss function. Current method include stochastic gradient descent that will find a new value at each iteration of the mean of the proposal distribution if you assume that it's a Gaussian distribution, and the covariance. And existing relevant methods include two variants of Langevin diffusion. The first one has been proposed by Welling and Tay in ICML 2011, which consists in finding a new value for the mean and the covariance, going in the opposite direction of the gradient of the log posterior distribution. A recent proposal developed by Zhang and colleagues in iClear 2020 uses cyclical learning rate and the Langevin diffusion to compute a new proposal at each iteration. What we propose is to use a simple averaging procedure. So if you consider that your covariance as a diagonal structure, then the mean and the diagonal standard deviation at each iteration will be computed as an average of the last snapshots of the Bayesian neural net and the current iterate. A recent improvement of that method has been proposed by Maddox and colleagues in 2019 in their SWAG paper, and consists in assuming that the covariance matrix of the proposal distribution has a low-rank plus diagonal structure and depends on the gap between the current estimate and the average estimate, the running average estimate. This leads to our new method to find those hyperparameters at each iteration. So this is called HWA, and at each iteration k, it takes as input the current estimate of the gradient of the loss function, which is the elbow, and computes new estimate for the mean and the covariance using simple stochastic gradient descent method. And at each cycle, if the number of iteration is a multiple of this length cycle, then you update a new running estimate for the average. I'd like to take a few seconds to explain why averaging would work in either deterministic or Bayesian neural net. The support for that will be extracted from the recent paper by Fort and colleagues called Deep Ensembles, a Loss Landscape Perspective. So it has been shown extensively that ensembling would lead to better generalization. I can cite either the fast geometric ensembling paper by Garipov and colleagues, or the SWA paper by Ismailov and colleagues, and contrasting with the version inference that would lead to mode collapse. Here, we believe that intuitively ensembling several model estimates would lead to better exploration of the loss function, or in our case, the posterior distribution. Some numerical results on MNIST and CIFAR using LeNet5 or a Bayesian variant of VGG shows that our method in red matches or sometimes is better in terms of accuracy than state-of-the-art method like SGLD or CSG MCMC. Thank you very much. You can write me an email if you have any questions.